Hi, we are at module 40 now. In this module, I am going to design the data path elements in Verilog. So for the GCD problem, in the last module I left off at a point where the gray box description of the data path inside the GCD module was ready, and in this module I am going to show you how to write the various data path elements, and in this video we will finish the data path description of the complete design. So let us switch to the Verilog description. So one of the things that I did not do earlier is I wrote all of this, how do I know the syntax is correct or not. So I did not check it earlier. So the first thing I am going to do is take the description that I had for the GCD machine itself. This is my GCD machine, and I am going to just run. So I do not have a test bench right now. So you can see that there is no test bench, right? It is an empty test bench, and I just clicked run, and when I clicked run I got several errors, right. Let us see what the errors are. The first error says unknown module type controller, the second error says unknown module type data path. Of course that is expected because I said controller C1 data path D1, and I did not give any description for data path or the controller yet, and it said these modules were missing. Now let me go and look at the file called datapath.v. This is actually giving the description for the data path, and the data path has several things like subtractors, mux, register and comparator. So one thing I can do on the EDA platform is I can say go and use data path v also. So compile data path v also when you compile the design.sv file. So if I save that and run it, at least the data path complaint should not happen. So let us go and look at what complaints we got this time. So it says there is still an unknown module type called controller. We have not written the controller, but now the compiler looked at the data path. In the data path we had 2 subtractors, 2 muxes, 3 registers and a comparator, and we have not designed those so far. So instead of writing all the Verilog and then compiling in one go, I am writing small pieces of Verilog. I will get it compiled so that if there are any syntax errors, I will fix them right away. So the only errors that I have are the references. So I do not know what, so let us see what are these things. The comparator is referenced once, controller is referenced once, mux is referenced twice, register is referenced thrice, subtractor is referenced twice, and these are not descriptions that I have given yet. But that is okay, there is no harm in this. So I am now going to write the design descriptions for multiplexer and whatnot. So let us look at the data path once more. So the first thing I need is, so let us start with the multiplexer because it is the easiest. So I will cut and paste the design description that I need. Remember, for the multiplexer I said it is the output, select line, the 0 pin and the 1 pin. So these are the 4 things that I need. So I am going to design something called mux.v. In mux.v, so the module name is supposed to be mux. So I have cut it, I did cut and paste so that I know exact order in which I am supposed to give things. So this is supposed to be, the first one is supposed to be the output, so I can just call it out now. The next line is supposed to be the select line, I will call that SEL. Then the input on pin 0 and the input on pin 1. So this is, these names in 0 and in 1 are local to the multiplexer's description, that is it. We have done this before, in 0, in 1, select and output. These are the 4 ports that the multiplexer has. So let us do the descriptions for the ports. So output, so out is actually a 7 to 0 output. So the reason why, so output, remember this is supposed to take the same width as the data path elements, right. So again if you go and look at the picture, this picture here says this is a 8-bit line and this is a 8-bit line. So this multiplexer is going to select either this 8-bit line or this 8-bit line and present it as the output, which means the design description for the subtractor, the multiplexer, the register, all of them will have 8-bit values. So I am going to do that right now. So the multiplexer has an output which is a 8-bit value. There are 2 inputs in 0 and in 1 which are again 8-bit values, and there is a single bit line called select, which is supposed to select either in 0 or in 1. So this takes care of the wiring connections. So now we need to write the design description for it. I am going to use the familiar always block. So always at select or in 1 or in 2. So what this is going to do is, if either the select changes or input 1 changes or input 2 changes, this is a combinational circuit, output is supposed to change, right. So this is what we needed. So the interesting thing is that in 1 and in 2 are now 8-bit values. So in 1 is a 8-bit value and in 2 is a 8-bit value, and if any of the bits in input 1 changes, or if any of the bits in input 2 changes, oh I am sorry, it is supposed to be in 0 and in 1. So any of the input bits in 0 or in 1, if they change, I want the multiplexer's output to reflect that. So instead of specifying each and every bit as in 0 of 7 or in 0 of 6 or in 0 of 5 and so on, if you just give the whole vector, the always block will get triggered if any of the bits in the vector changes. So if in 0's a bit, even if one of them change, then the multiplexer will react to that and the output of that will change. So that is the sensitivity list. So in the sensitivity list, if I have a vector, I can specify the whole vector. If in this case multiplexer is supposed to pick the whole thing, so I specify the whole vector. So let us go and write the design description. So if select equals 0, then we want output to follow in 0, else we want output to follow in 1. It is as simple as that, right. So that is all we need. We need output select in 0 in 1. So this is, I am put it in a file called mux.v. Let me save it. Let me go back to the design file now and run it. Now at least I should get one less error. Let's see the errors that are coming up. Okay, so I didn't include mux.v, so let me include mux.v. I'll save this, and if I run it, so you can see that this error that I had earlier, that multiplexer is referenced 2 times, that error is not coming anymore. So we have a comparator, controller, register, subtractor. We know that these are not defined yet, but the error on multiplexer is gone. Also, thankfully, I didn't make any mistake in multiplexer either, so there is no mistake that is coming up here. If I made a syntax error in multiplexer or something else, then the error will come up here also. So we don't have that now. Let us move to the next design. So I am going to call that register. So register is the next thing that we needed. Again, if we go and look at the data path, let us see what the register is supposed to have. Register is supposed to take clock, reset, input, load, enable and output. Again, as before, let me just start with a cut and paste so that I will have the design description ready, the interface description ready. So I want a module called a register, which is supposed to take clock, reset. I am just going to call these other lines with local names which are different. So I am going to have output, load, enable and input. So these are the different things that I need. Again, I need to go and specify whether these are inputs and outputs and whatnot. So clock and reset are inputs. Then we have in itself as a 8-bit value. Load, enable is again an input, but that is a single bit input, and out is a 8-bit value. So I will start with that. So this is fairly straightforward. We have that, and once we are done, so what we need is we need to specify a bunch of things. So what do we need? We need to specify that the register on either reset or on load, right? It's supposed to take, it's supposed to do different things. So and we decided that the whole thing will be a synchronous circuit. So there is nothing which is going to be asynchronous. So what I will do is I will take always at pos edge of clock, always at pos edge of clock. So at this point, so I already know that the clock is triggered, which means at this point if I sample reset, if reset is 1, I want the output to be 0. So this is always a safe thing to have. If reset is 1, output is 0, else if load is 1 or load enable, I called it LDEN, if load enable is 1, then output is supposed to follow the input. So let me reduce this, output is supposed to be the input itself, which I called in. And if you do not put an else clause here, it is okay, because if you do not have an else clause, it means remember the old value which is given. So the old value is whatever the output was, it will just remember it. So this is just a register which takes a parallel load as a parallel input as a, so it has a 8-bit input which it will take as a parallel input, and it is going to give it out as a parallel output. The only thing is if reset is 1, the output is initialized to 0, else if load enable is 1. So there is a priority in order in which things are checked. If reset is on, it will override everything else. Otherwise, if load enable is on, the output will follow the input, and this is the end of this module description. So it is as simple as that. So it is not very hard. If you see that the way in which I am taking things is very organic, it is taking like one small step at a time without you having to worry about everything. Once you have the hardware picture with you, I am writing Verilog in small chunks. So I can now go and add register.v in the design file, right. So I am including that in the compile options, and I am going to run it. So again, this run is only an empty run because I do not have a test bench or anything. So all I have is just the design descriptions. I am just ensuring that there are no syntactical errors. So again, I notice that the registers reference is gone. So the register is, and it also looks like register had no errors. So far we are good. Now let us go and write the subtractor and the comparator. So again, let us go and look at what the subtractor is supposed to take. The subtractor, I am expecting that there are 2 inputs and there is an output. So even though it is called TA out, TB out and T1, again if you go and look at the picture, TA out is actually an input to the subtractor, and TB out is actually an input to the subtractor. So they are called A out and B out because they are coming out of the registers. So there are 2 inputs followed by the output in the subtractor. So let me copy that. So module subtractor. So I am going to call this input 1, input 2, output. Simpler names. So I do not need to carry the names from the external world. I will just give internal names which make sense. So this is a combinational circuit, and in this combinational circuit, if it is supposed to take the input on the first pin and take the input on the second pin and subtract one from the other, that is all it needs. So what I am going to do is I will declare them whether these are inputs and outputs and whatnot. So input in1 and in2 are both inputs, I declare them as such, and out is an output. And since this is a combinational circuit, I am going to write it as always at in1 or in2. If either one changes, the output is supposed to change, right. And now I am going to show you something which is slightly different. So I am going to write out as in1 minus in2. This is something that I have not introduced to you so far. So what I did now is, so I can go and write a subtractor. so I can go and do a design description for a subtractor which is very careful. I pick the basic gates and whatnot, but Verilog also has what is called a behavioral description. So in this case the behavior that we want is in 1 minus in 2. So this minus stands for subtraction. Verilog allows you to do that, even though in your homework that I have explicitly said go and design a adder which will go and instantiate half adder and full adder and so on. Technically if you did out equal to a plus b, right, so that is acceptable in Verilog. So here in 1 minus in 2 it is supposed to be a subtractor, and tools can actually infer this and say that, oh, this is a subtractor. If there is a subtractor description available, it can instantiate a subtractor directly. So this is something that tools can do. So from Verilog, when it looks at minus, it will just interpret this as subtract one from the other, and I am going to leave it at that. So I have not done a design of subtractor which uses the basic gates. So I have taken it at a slightly higher level. For a programmer who is comfortable, this is probably better because Verilog can actually pick the appropriate set of gates and optimize it and so on. So you can give it to a what is called a synthesis tool. A synthesis tool, when it sees in 1 minus in 2, will go and pick an appropriate subtractor based on the constraints that is given. So this is not something that we have talked about so far, but I have kept it at a level of abstraction which is high, rather than instantiating basic gates and so on to get a subtractor. So let me now save this, and as before I will add subtractor.v to the design. I will save it and run it. So just to ensure that there are no mistakes in the subtractor. So it is always a good idea to ensure that anything that you write is actually syntactically correct, because otherwise too many errors will accumulate and so on. So again the subtractor's warning is gone, and there is no error on the subtractor right now, and it looks like the subtractor itself is having no error. So somehow magically when I am typing code, it looks like there is no error that I am making at all, but this comes with years of practice and experience. So you may make mistakes when you design things, and it is better to actually go and check each one of them out to ensure that there are no syntactical or semantic errors. So in this case I know that input and input 2, both of them should be on the sensitivity list, and minus will work and there is a semicolon needed. So I know all of this from years of Verilog design. So I have put all of that right now. So the final beast that I am going to design is the comparator. So let us go and look at what the comparator is supposed to do. The comparator is supposed to take 2 inputs and it is supposed to give 3 individual bits as output. So let me copy the design description. So comparator module comparator is supposed to take several inputs. So let me call them A and B here, because it is supposed to be comparing A and B, right. So it compares 2 numbers A and B and gives 3 bits, A greater than B, A equal to B, and A less than B as output. So let me put the design description. So A and B are 8-bit values and they are inputs. A greater than B, A equal to B, and A less than B are all outputs, and they are single bit outputs, right. So this takes care of the design interface description. So now I have to go and write the comparator itself. So again I am going to use the always block for this. Either A changes or B changes. If either one of them changes, then the comparator is supposed to change the output. So here what I am going to do is I am going to do a series of comparisons. Again I am going to introduce something new in Verilog that you have not seen so far. So I am going to check if A greater than B. This is just like what you do in programming languages. So instead of comparing them bitwise, I am letting Verilog use the comparator operator. So the comparator operator A greater than means A and B are interpreted as, so these are 8-bit values, right. The 8-bit interpretations of A and B are used directly, and so there are 2 things. when the compiler in the simulator runs, this greater than is a simple operation. You take the 8-bit value and compare with the 8-bit value, but later when we want to infer a circuit for this, the synthesizer will go and look at A greater than B and generate a appropriate circuit for this. So if A is greater than B, then we know that we want these three names, right. So again I am going to show you something new here. So I want these three values, I need only one of them to be on. So I know that this A greater than B should be on, A equal to B, A less than B, these two should be off. So one way to do that is I am going to put something here which is new to you again. So on the right side what it says is I am giving a 3-bit vector and they are on binary. So this 3 means I am giving you 3 bits. So I am giving you 3 values, this 1 0 0 is 3 values, and these 3 values what they mean is they are interpreted as bits. So let us look at the left side versus right side. So if A is greater than B, I want A underscore greater than underscore B to be on. So these 3 values on the left side will take the corresponding values on the right side. So A greater than B will take 1, A equal to B will take 0, A less than B will take 0. So that is what this statement is supposed to be. On the left side we have grouped 3 bits together by putting what is called the set bracket. On the right side I have what is called a bit vector. The bit vector is a 3-bit vector. So this B says it is a bit and this 3 says it is a vector, and the values that are supposed to be in the vector are 1 0 0. So that is the first line. So if A greater than B, then it is this, then I am going to do else if, so I can now check if A is equal to B. If A is equal to B, then we have again the same thing. I am going to cut and copy now, right. Instead of 1 0 0, my vector is 0 1 0. Finally, if this is also not true, then it has to be the case that A is less than B. So in which case I will put 0 0 1. So let us see what we have done here. So maybe I will reduce the font size so that you can see what it is. Yeah, so let us see this. Always at A or B, if A is greater than B, then these 3 single bit values will take 1 0 and 0 correspondingly. If else if A is equal to B, then these 3 bits will take the corresponding value 0 1 0, and otherwise they will take 0 0 1. And so I am going to use the less than symbol here, so I am going to use this statement which is a signal assignment statement. So I will talk about this later, and we are done. So this takes care of the comparator also. So if A or B changes, then this always block is evaluated and you will get one of these output bits to be a 1. So let me again save this, and I am going to add comparator also as a file. Go back to design, save it and run. So hopefully the controller, nice. So the only thing that is missing, so we have compiled all of these and it says the unknown module type controller. It looks like the comparator itself again has no mistakes. So what we have done is the data path was instantiating 2 subtractors, 2 multiplexers, 3 registers and a comparator. For each one of them we have given the design descriptions. So there are 4 design files which takes care of each one of them. The only thing that is left out is the controller itself, and the controller, so we have the state machine. What we will do in the next module is we will take the state machine and I will show you how to write the state machine as a Verilog code. So far we have done quite well. So we have started from a vague algorithmic description of the problem, which is the Euclid's algorithm. That algorithm itself may be new to you, but if the algorithm is given to you, from there we identified what are all the different components that are needed. We took all of the components and we did a hardware diagram. The sequencing of the hardware is still something that we haven't figured out. We need the state machine, which we did as a picture. We need to go and write the Verilog for it, and we have done a top down design of Verilog. Starting from the design description, we put the controller in the data path. For the data path, we needed the subtractor, the multiplexer, the register and the comparator. We have designed all of that. The data path design is complete now, that is it. The data path design is over. The only thing we need is, we need to put the controller, the state machine for the controller. Once we write the Verilog code for that, the overall description is done. Then we can write a test bench and test it and ensure that the whole thing is working fine. So it may seem to you that this thing is magic and all of these are working nicely and so on. It's just that I have taken a lot of care in drawing the diagram, taking the diagram and putting it into Verilog, ensuring that all the connections are in the proper order, and Verilog syntax itself did not come in my way. If you are a new programmer in Verilog, all of these could be daunting. They are not going to be simple tasks that you can do in a short period of time. You will take a lot more time to do it, but that is okay. So you have seen me. Now what I'll put all these files in the folder later. You can take these and play around and see how each of these descriptions are provided to you, and you will also be able to come up with these things once you practice. So one thing with programming languages is that you have to keep practicing with more and more design problems. Only then the Verilog, the language's syntax and various semantics and so on stick with you. So if you learn and then if you forget for some time, if you don't practice, after 1 month or so you will not remember anything at all. You have to keep practicing programming languages specifically so that you remember it well. So this is just like playing a musical instrument or things like that, where unless you practice continuously, you may get out of touch. So this brings me to the end of this module. In the next module, we will see how to design the state machine, and finally we will put the state machines, the controller and the data path together, and we will write a test bench. The test bench will test the GCD machine. So thank you, and I will see you in the next video. Bye.